Dear students, today we will be discussing about design of grid connected PV system. So, in design of grid connected PV system, what are the different steps? And the first step is preliminary study, second step is design of the system, and third step is performance analysis. Okay? So, in preliminary study, what are the work components includes? Study of geographical setting of the location. Okay, we must know the geographical condition of that particular locations where we are going to install the solar PV system, and then analysis of climatic condition. So, we must analyze the climatic condition, what are the different radiation levels, sunshine hours, and all those radiation parameters, and then selection of the systems. So, what kind of systems is appropriate, maybe standalone, maybe grid connected system, and what capacity. Then selection of PV technology, the kind of modules and others. So, under design of the systems, primarily it includes selection of components like modules, inverters, cables, combiner box, and others. And this PV array inverter matching is very crucial for design of this grid connected PV system. So, you have to match those output of the PV module and input of the inverter. Okay? So, other parameters like current, voltage, power, and also we need to find out the appropriate number of modules, appropriate numbers of inverters required for a particular capacity. Of course, we need to learn cable loss calculation, then shading analysis, and under performance analysis we need to do the system energy production, the amount of energy will be produced by the PV system, performance ratios, then system losses. Of course, this component will be discussed in the next class. So, prior to designing any grid connected PV system, a designer must know the geographical setting of the location and must visit the site to determine the solar access for the site, to determine whether any shading will occur and estimate its effect on the system, to determine the orientation and tilt angle of the roof or a particular site, to determine the available area for the solar array, to determine whether the roof is suitable for mounting the array in case of roof mounted system, to determine how the module will be mounted on the roof or the site, and determine where the inverter will be located, and to determine the cable route and therefore estimate the length of the cable runs. Okay? So, how long we need to maintain the cable length. After this is done, then what we need to do as a designer. So, this designer will estimate the available solar irradiation for the array based on the available solar irradiation for the site, and then tilt is known for a particular location, then orientation and effect of any shadows. Okay? So, by analyzing this information, so amount of solar radiations to be received by the solar plant will be estimated. In the next phase, analysis of climatic condition of the location is very important. Normally, in order to get those meteorological data, the government meteorological departments provide those data. Otherwise, if it is difficult to get those data from the government departments, we can rely on some open sources. So, this location wise climatic data can also be collected from NASA meteorological department available online. So, this website we can access and we can download the required data. The following parameters are considered for analyzing climatic scenario of a particular location. Number 1 may be monthly average daily normal radiation, monthly average insolation incident on a horizontal surface, monthly average clear sky insolation or clearness index, monthly average daily hours, daily sunshine hours, monthly average wind speed, monthly average relative humidity, monthly average air temperature, monthly average rainfall. These informations are required. Already we have discussed many more techniques how to investigate many of the parameters mentioned in this list. So, now come to the design of the system, the selection of the components. Okay? So, system design should follow appropriate standard. The standard may be BIS standard, may be IEC standard, may be IP standard, IS, EN, SS. There are many standards, but country wise these standards may vary. Okay? So, components with applicable BIS or equivalent IEC standard or MNRE specifications what is used in India are something like for solar PV modules, IEC stands for International Electrotechnical Commission. Okay? So, they have a standard 61215 or Indian standard 14286. This standard is used for inverter IEC 62109-1 or 2. This configurations are used, and for cables this BS stands for British standards and EN stands for European standards 50618. This kind of cables standards are used. For connectors also there are specific standards. There is IEC 61730 and aerobox protection, it is IP 65. Then module mounting structure IS Indian standard 2062 or maybe 4759, or lightning arrestor which is very important component of a grid connected PV system. Its standard is about IEC 62561 series, and weather monitoring stations are also attached in a grid connected system. So, it has got one standard. Then SCADA systems also has got standard, that is IEC 61850, and fuses, as you can see there are standards. Okay? IS Indian standard or EN, that is European standards. Okay? So, these standards are used normally for a grid connected PV system. Now, come to the designing of grid connected PV system. We apply the principle of energy balance paradigm. So, here what happens, the energy which is generated by the PV arrays has to be equal to the consumed energy during 1 year. So, this paradigm is normally applied for designing a grid connected PV system. So, let us learn how this can be calculated. So, the energy yield at the DC side is given by E is the energy, yearly energy, Y stands for yearly and DC stands for DC. Okay. So, this is something like if we have these PV modules, there are many modules, okay. So, this becomes array, So, output of this array, this is something like DC. Okay. So, this is DC energy EDC, okay, or you can write EDC. Okay. Since it is yearly, so we will write Y. Okay. This is something like that. This energy we are talking about EDCY. Okay. This is something like A total, this total area of the modules, integration of GME is the intensity of solar radiation and eta is the conversion efficiency, right. So, this will give yearly energy yield in the DC side. So, this is the energy yield. So, this A total is related to the area of one module, right. So, A total will be NT multiplied by AM. What is NT? NT is the number of modules in that particular array. Okay. Once we know this information, then we can use this A total and that can be applied here and we can calculate EDCY, okay, or yearly energy yield in the DC side, right. So, the required energy balance, what we can do, EDCY is equal to ELY, this part is something called load, okay, load side. multiplied by SF. This SF is nothing but charging factor that usually assumed to be 1.1, right. So, we equate this EDY is equal to ELY, that is load side energy, and this is your charging factor. Okay. So, once we equate this, and if we substitute this expression here, okay, and also we use this equation 2 here, okay, then we can simplify this equation 3 as something like this. Okay. So, we can calculate the number of modules required, that is NT. NT is ELY multiplied by charging factor divided by AM. Integration of GMT means this is radiation, that is normally global radiation integration for the entire year, and this is the conversion efficiency, right. Now, we need to know how are you going to connect those modules, because we need to connect parallelly and series. Okay. So, how this configuration will look like? How many modules will be there in series? How many modules will be there in parallels? Okay. So, as a whole, if we say the number of modules is connected in series NS and in parallel NP are denoted by NP, sorry, this should be NP, this is NS. Okay. So, NT is NS multiplied by NP. Okay. So, now we are not saying the number of modules connected in parallel and number of modules connected in series. Okay. We will learn how this can be done. And for example, if NT is 11 panels or 11 modules, it can be taken as NT is 12, because this is a odd number, because they can be installed as S into P. So, this may be 12 into 1, okay, or maybe 6 into 2, 12 in series and 1 in parallel, 6 in series, 2 in parallel. So, these kind of configurations may be adopted. Okay. So, best combination has to be find out what will be the best which give you the maximum power output. Okay. So, we will solve problems to understand this knowledge for betterment of the design of the PV grid connected system. So, the power on the DC side at standard test condition is given by something like this. Okay. So, under test condition it will be something like this, okay, which is equal to NT into P MPP, maximum power point in STC. Okay. So, what is the condition? PDC maximum inverter has to be greater than PDC at STC. Okay. So, once we know this value, we must know this value has to be less than this P inverter DC max. Okay. So, there are some ratings of inverter. So, we must know the ratings of the inverter. So, that will dictate us how to match this energy. Okay. So, we will discuss in the coming slides. Further, the nominal DC power of the inverter should be approximately equal to the PV power at STC. Okay. This is also one condition. So, PDC at nominal power is equivalent to PDC STC. This is also one condition has to be met, right. So, in practice, the nominal DC power of the inverter is selected slightly below the PV power at STC. Okay. So, depending upon the climatic zone, because of the different irradiance distribution. So, this is very, very important. Also, for PDC at nominal condition has, if it is less than 5 kilowatt peak, then single phase inverters are used, while if it is more than 5 kilowatt peak, so this is kilowatt peak, 3 phase inverters are advised. Okay. So, this kind of design methodology we have to adopt for designing a system. So, let us have a look about the specification of modules and inverter. Okay. So, if we talk about the specification of a module, we can see, for example, we can consider a module having no output power or watt peak is 300, okay, and efficiency is 15.10, and voltage at P max, that is in VMPP, in voltage is 36.6, and current at P max is 8.20, and then open circuit voltage VOC is 44.8, short circuit current is 8.71, okay, and power tolerances are given, and also NOCT, nominal operating cell temperature, is 47 plus minus 2, okay. This is also important, and these components are very, very important because this performance of PV modules deteriorates with respect to temperature and insulation, okay. So, if temperature increases, this performance decreases, okay, and solar radiation if increases, then performance increases, but no, if it increases further from the standard test condition, then temperature rise will be there, and that causes lot of problems in the PV modules. So, this temperature coefficient of P max is something like this, 0.4048, temperature coefficient of open circuit voltage is something like this, and temperature coefficient for current, short circuit current, is something like this, okay. Let us also learn about the specification of an inverter, okay. So, in case of inverter, as you can see, maybe we can consider this inverter manufactured by Bonfiglio. So, here DC power input is 280 kilowatt, okay, and maximum DC voltage is 900 volt, DC current is 600 ampere, and this MPPT voltage range is 425 to 975 volt, okay. So, these informations are required while designing or matching this PV array and inverter, okay. And output voltage also required, maximum AC power is 250 for this configuration, and then voltage is 270 to 300 volt, then AC current is 540 ampere, then maximum efficiency is 98.3%. So, for example, if we design for a capacity of 2 megawatt, okay, and single inverter will give 250 kilowatt, then how many inverters will be required? It will be 8 inverters, right, 8 inverters, okay. So, that way we can do a lot of design calculations, okay. So, what I am saying, 2 megawatt is 10 to the power of 6, okay, watt, okay, kilowatt means again 3, okay, maybe 2111 kilowatt, okay. If we divide it by 250, it will be 8, okay, it will be 8. So, that is how we need 8 inverters for a 2 megawatt capacity grid connected PV system, okay. So, now come to the matching of inverter and array, okay. So, how we are doing it, okay. So, it is important to find out the most appropriate combination of module and inverter by considering the local operating conditions, okay. The voltage, current and power rating of module and inverter are the 3 criteria which ensure the proper matching of the system in terms of performance and safety. This is very, very important. What we are doing actually, voltage, current and power ratings has to be matched, okay. The important steps related to matching of inverter and PV modules are something like number of modules in a string, how many modules will be connected in series. When it is a string, that is a series connection, and then maximum number of strings to match with inverter input, right, and matching of the power rating, okay. So, these 3 components are very, very essential for designing. Now, what we will do? We will do the number of modules in a string, that we will try to calculate now. The first is to determine the lower and upper limit of a string, that is the minimum and maximum number of modules that can be connected in series. that we need to find out. So in order to find out this, we must calculate the maximum and minimum operating temperature. So how we will get the minimum and maximum operating temperature? By observing the particular place temperature fluctuation. Okay? So maybe in winter it is minimum is 5 and in summer maximum is 38. So if we know this temperature variation, then from that we can calculate what will be the minimum and maximum operating temperature of a PV cell. Okay? Then we need to calculate maximum and minimum effective voltage of the module. So what will be the effective voltage of the module? That needs to be calculated once we are done with the maximum and minimum operating temperature. So how to calculate minimum and maximum operating temperatures? So as I said, by knowing the ambient temperature of a particular location, NOCT, nominal operating cell temperature of the PV module, and the incident solar radiation at that location, the module operating temperature can be calculated as this. Okay? So we want to calculate this T operating, and we must know T ambient, and then NOCT is required. Okay? So this is a standard formula you can use, and Z is solar intensity, right? So the maximum operating temperature and minimum operating temperature can be calculated using this equation by considering recorded highest and lowest ambient temperature of a particular location. So if we know this temperature fluctuation, from that we can calculate what is the minimum operating temperature and maximum operating temperature, right? Let's move on to the next slides. So here we need to calculate number of modules in a string. So minimum and maximum effective voltage of the module, how to calculate it? So we can use this equation. So V minimum effective is equal to VMP STC. Okay, this is maximum point under standard test condition in the module side, and gamma P is temperature coefficient for this voltage, and T operating maximum, because already we know what is the operating maximum temperature. Okay, and then STC condition is 25, and for calculation of V max effective, then we need to know what is open circuit voltage, okay, under standard test condition, and we have to use this temperature coefficient for open circuit voltage, and we know this T operating temperature by knowing the climatic condition of a particular location, and TSTC is known to us. Okay. So we can note that it is very important to keep in mind that the output voltage of the array should not fall outside the inverter's MPPT voltage range. Okay. So this is very, very important. Okay. This is one of the important design observation. So now let us know how to calculate this M string, that is minimum number of modules in a string. Okay. So by using this equation we can calculate the minimum number of modules in a string, okay, or minimum number of modules which can be connected in series, right. So for this we need this inverter input voltage and then minimum effective voltage, okay, which already we have discussed. Okay. So please note that there is a voltage drop which occurs when the generated electricity flows from array to the inverter. Okay. So voltage drop will be there. Okay. Therefore, during the calculation of the lower limit, a 22% voltage drop needs to be considered, okay, for V min effective, and a safety margin of 10% should be considered for V inverter DC. So when we are doing very precise calculation, we need to remember these two conditions. Okay. So how we are going to use those values for calculation of minimum number of modules in a string, right. So we are also interested to know the maximum number of modules in a string. Okay. So in order to find out the maximum number of modules in a string, we need to rely on this V inverter DC max. So, here it was minimum and it was maximum, because MPPT variation will be there, okay, minimum to maximum, that voltage we need to use. And this Vmax effective, what already we have discussed, that can be used to calculate this maximum number of modules in a string. Okay. Please note that for calculation of Vmax effective, this value, the open circuit voltage is considered, since there is no voltage drop. Okay. So, this is important, but for calculation of inverter voltage, that is maximum voltage, is 5% safety margin is applied, right. So, this information need to be keep in mind while designing the grid connected PV system, especially for minimum number of modules in a string and maximum number of modules in a string. Okay. So, now let us use this current rating. Okay. This current rating of modules has to be matched with the inverter input current rating. Okay. In order to determine the maximum possible strings to be connected in parallel. So, so far what we have discussed, the number of modules to be connected in series, okay, minimum number of modules to be connected in series and maximum number of modules to be connected in series. Now, we must know the number of modules to be connected in parallel. So, once we are decided with this series connection or strings, then we have to connect it in parallel. So, this is the procedure how we can do it. Due to the variation in operating temperature, the value of short circuit current of the module also differ from its STC value, that is obvious. Okay. So, if we need to account those variations, then we need to use this equation. ISC effective is something like ISC, that is short circuit current under standard test condition minus this temperature coefficient for this short circuit current multiplied by T operating maximum minus TSTC. Okay. So, TSTC is normally 25 degrees C. Okay. So, these are the values what this parameter stands for. So, gamma SC short circuit temperature coefficient, gamma P maximum power temperature coefficient, and then gamma VOC is open circuit voltage temperature coefficient. Okay. Now, also we must know the maximum number of strings to be connected in parallel. Okay. So, this is the equation we can use for calculation of maximum number of strings to be connected in parallel. Once we know this I inverter DC and then ISC effective, which one already we have calculated here. So, if we substitute these two values, then what we will get, that is a maximum number of strings to be connected in parallel. Okay. Now, what we need to do, match the best combination of strings and arrays to get the maximum DC output, right. The maximum DC power output of the PV array should be always less than or equal to the input DC power of the inverter. This condition is very, very important. Okay. The maximum DC power output of the PV array. Okay. So, you have this PV arrays. Okay. So, we have calculated maximum power output, okay, or say I will write P max, okay, and that will be DC is always less than the input power of the inverter. Okay. So, in our case, it is input power of the inverter is 280. Okay. So, this is input power of inverter I and V. Okay. So, this is something like that. Now, for example, so if in a calculation, if we know the minimum number of string and maximum number of string, okay, and number of arrays based on our calculations, okay. So, maybe 59 we got, okay, but this is fixed, because see rating, if we consider without derating of the module, say 300 watt peak module we have considered, right. Then here if we multiply by 16 into 59, say number of string per array is 59 and number of modules is 16, right. So, if you multiply 16 multiplied by 59, then multiplied by 300. So, what we get is something like this value. So, as already we know, this maximum input power is 280 kilowatt, input power of the inverter is 280 kilowatt. So, it should not be more than that. Okay. So, it is more than that, so it is not feasible, right. So, if we take 58 number of strings per array, so it will be 270, it is a feasible case because it is less than 280, what is discussed here in the second bulleted point, right. So, if we consider the maximum number of strings, that is 17, and if we take different strings or number of strings, say 55, 54, we can see which one is best fitted. Okay. So, this one is found the best fitted. Okay. So, we can decide based on the economics and the other conditions which one will be the best fit for the particular plant. Okay. Now, we need to pay attention about the cables, right, because this cable also consumes huge amount of power and cost. Okay. So, to determine the cross-sectional area of DC cables, we can use this equation. Rho is the resistivity, I is the current flowing through this circuit, and this cable length, and losses will be there, and we already know V MP string. Okay. And for AC cable, these equations are used. Okay. Of course, power factors are need to be multiplied. Now, we need to see the shading effect. When we are installing PV modules, we must know how are you going to install these modules. If shadow is occurring, then no, instantly we are losing lot of generated power. Okay. That means, if one module is shadowing others, then no, this shadowed modules are not generating power. So, this effect of shadow is very important, and we need to analyze it very critically. So, the minimum distance between two solar modules which is maintained in order to prevent mutual shadings are need to be studied. Okay. So, if we consider this module and this module, okay, what will be the appropriate distance between this top of this module and this position. So, we need to specify, so that shadow caused by this module should not hamper the functioning of this PV module. Okay. So, we can do a lot of calculations and we can come up with a solution, and it tells that no, this D has to be 3 into H. So, H is nothing but this height, and this is solar module tilt angle is theta here. Okay. And alpha is the sun elevation angle. Okay. And if you consider this LHH, so this LHH cos of alpha is also D, and this equation can also be used for investigating the distance between these two modules. Okay. So, tip of this and then bottom of these modules is D, right. So, let us now take an example, okay, so that you understand how this kind of problems can be solved. Okay. So, the example goes something like this. A solar plant is to be installed at say IIT Guwahati campus to meet the electricity demand of 2 megawatt at a solar insolation of 800 watt per meter square. Okay. This may be considered as global radiation. The manufacturer's output tolerance derating due to dirt and due to temperature of PV module are 5%, 5% and 0.5% per degree increase in temperature. Okay. So, DC cable losses are given, AC cable losses are also given. Okay. The inverter has a maximum voltage input is 900 volt, maximum DC current is 600 ampere. So, detailed specifications are given here, specification of the module and specification of the inverter. Okay. And also it is given that the minimum temperature and maximum temperature and solar peak hours of the sites are 5 degree, 38 degree and 5 hours. So, find out the total number of modules required for the plant, and also we need to estimate the DC output of the array. Okay. So, we need to solve this problem now. Okay. So, what I can say, this is T minimum is given as 5 degrees C and T max is given as 38 degree C. Okay. So, this power rating is 300 watt peak, okay, and voltage at P max is 36.6. So, these values are going to be used, and open circuit voltage is 48.8, short circuit current is 8.71, right, and these values are also required. Okay. These values are also required, and NOCT is 47. So, in our case NOCT we will use 47 degrees Celsius. Okay. And here in inverter, as I said, this is maximum power, DC power, that is input to the inverter is 280 kilowatt, and this is the output 250 kilowatt, right, and we will have DC maximum current is 600 and MPPT voltage range is 427 to 975 volt. Okay. These informations are required for solving this problem. So, let us first calculate, or first let me draw this diagram. Okay. This may be different, this is an array, and these are modules, solar radiation is falling here. Okay. And then we will have inverter, here. Okay. MPPTs are attached with it, and we will have, this is DC cable, and this is AC cable. Even datas are given for DC and AC cable and then losses. So, maybe we will not consider for this problem. Is a grid. Okay. So, we need to produce 2 megawatt of power, right. Now, this I is given as 800 watt per meter square, and since we have already discussed the expression for operating temperature, T operating is something like T ambient plus NOCT minus 20 divided by 800 into Z or I. Okay. Z or I. Okay. Solar insulation. So, this value is given as 800 watt per meter square. So, if we substitute 800 here, NOCT is 47 here, and T ambient is given as maybe 28 degrees Celsius. Okay. This is T ambient. So, if you substitute this 28 plus NOCT is 47 minus 20, okay, because these are same, both will goes off. Okay. So, this will be T operating will be 55 degree C. Okay. And also we must know this may be the derated PV output. Okay. So, now we will calculate derated PV output. Derated PV output. Derated PV output. So, how to calculate it? So, PV derated. So, derated will be how much? It will be P STC multiplied by this F may be temperature, derated due to temperature, F derated due to dirt, and F derated due to we have manufacturing tolerances, right. So, as we know this operating temperature is 55 degree, okay, and in our problem it is given that this rise in temperature, okay, 0.5% per degree rise in temperature is the derated factor. Okay. So, we know STC is at 25 degree C, then this operating temperature is 55. So, 55 minus 25, it will be 30 degree C. Okay. So, if we can operate at 25 degree C, then there is no decrease in performance of the PV modules. Since it is more than 25, then this rise in temperature as need to be considered. As we understand that every degree rise in temperature, there is a decrease about 0.5%. Okay. So, what we can do in order to calculate this F temperature, so this will be 1 minus 0.5 multiplied by 30 divided by 100%. Okay. So, what we will get here is 15, okay, it will be 0.85, right, 0.85, and for dart it says that 5%, so it will be 95%, okay, and it is 5% again, derated factor is 5%, so it will be 95%. Okay. So, if we substitute here, and TSTC is 300 watt peak, already we have discussed, and this is 0.85, and then we have 0.95, and then we have 0.95, then what we will get is a PV derated. So, this is calculated to be 230.137 watt. Okay. So, this is nothing but PV derated. Okay. PV derated. So, this value is required. So, this may be 2, we can write. Now, in the next page what we can say or what we can calculate, because already we know T min and T max. Okay. So, what will be the T operating minimum? Okay. T operating minimum we can calculate T ambient. Okay. So, minimum ambient plus NOCT minus 20, then we have 800 multiplied by 800. Okay. This will goes off. This NOCT is 47. Okay. So, 47 minus 20, and this is minimum is 5. Okay. So, 5 plus 47 minus 20. Okay. 47 minus 20. So, this will be 32 degree. Okay. Similarly, we can calculate what is T operating max. Okay. T operating max will be, we have 38 degree C which is given, plus, because this will goes off, 47 minus 20. So, it will be 65 degree C. Okay. This is C. So, these values are known to us now. These values are known, and TOP mean is known to us now. Okay. Now, next step, what we can do, we can calculate what is V minimum effective. Okay. So, we will calculate V minimum effective. So, already we know V minimum effective, okay, which has already been defined. So, we will use this equation VMP STC minus, we have gamma P, then multiplied by TOP max minus TSTC. Okay. So, this will be something like this. So, we can substitute this value. V MPSTC is nothing but, you can go back to the last slides. So, this is something like 36.6. So, this value is required. to calculate V minimum effective. So, this is 36.6 minus gamma is given as, so gamma P also we can calculate, or we can take it, this is 0.4048. So, 0.4048 here, 0.4048 divided by 100. So, this is under this, okay, this is under this, okay. So, T operating maximum is how much? 65, okay. 65 minus TSTC is always 25, okay. So, if we substitute this value, then what we will get? A value of 36.43 volt, okay. This is V minimum effective, okay. So, once we are done with this, the next step is to calculate V max effective, okay. So, what was the formula? VOC STC, okay, open circuit voltage under standard test condition of the module, and then gamma VOC temperature coefficient. So, I will write here TOP mean minus TSTC, okay, right. So, this value open circuit voltage we have to take it from here. So, this value 44.8 and this value we need to take, okay. So, this 44.8 we need to substitute 44.8 minus 0.2931 divided by 100, and this minimum is 32 minus 25, okay. So, if we do the calculation, this V max effective is found to be 44.779 volt, okay. So, V max effective, right. This is known now, okay. So, next step what we need to do is the minimum number of modules to be connected in series and maximum number of modules to be connected in series. So, how to do that? So, we can use the equations what we have discussed. So, this M string, that is minimum, okay, which is nothing but V inverter DC, that is minimum, okay, and then we have V min effective, okay. So, I have to go back to this specification part. So, here this is the V inverter voltage, that is minimum, that is 425, okay. This 425 need to be used here. So, 425 and then we have V minimum effective, already we have done it, that is 36.43, which is equal to 11.67. So, that is equivalent to 12, because there has to be a whole number, okay. And maximum number of string, that is max. How do we define it? Already we have the equation V in DC, that has to be maximum, okay, maximum voltage divided by we have V max, already we know effective, okay. So, this value is how much? We will go back and see, this is 975 volt, okay. So, this is 975 and V max effective is 44.779, and which will give you a value of 21.77. So, which is equivalent to 22, okay, is 22. So, what I have done here, so first we have calculated operating temperature, then we have calculated derated power output of the PV array, okay, and then since we know these values of the derated factor, so we have used it while calculating this derated PV output, and then our attempt was to calculate T operating minimum temperature and operating maximum temperature. Okay. So, this is found to be 32 and 65, and then we have calculated V minimum effective and V max effective, and we have calculated number of modules to be connected in series, minimum number of modules to be connected in series, and maximum number of modules to be connected in series, okay, which is found to be 12 and 22. Okay. So, our next calculation will be the calculation of ISC effective, because we need to now know the number of strings to be connected in parallel. Okay. So, we know the expression ISC STC minus gamma ISC multiplied by, we have TOP max minus TSTC. Okay. So, what is the value of ISC STC? We will go back again. This value is 8.71. Okay. And also temperature coefficient is 0.0442% per degree C. Okay. So, this is 8.71 from the specification table, and same from the specification table, and we have 100, and then we will have 65 minus 25. Okay. And this is found to be 8.69 ampere. Okay. So, ISC effective is something like this. Now, we need to calculate the maximum number of strings. So, maximum, now we will calculate maximum number of string to be connected in parallel. Okay. So, for that we have the equation S max, which is nothing but I inverter DC divided by ISC effective, which is calculated just now. Okay. So, this value we need to use here, and this is already given in the specification table. So, what is this ISC DC value? I inverter DC value, it is nothing but 600 ampere. Okay. So, if we substitute 600 here, then ISC effective is 8.69, then it will be about 69.04, or it is equivalent to 69, right. So, now what we have calculated is the maximum number of strings to be connected in parallel is 69. Okay. Now, we have to match it. Okay. So, we know now the minimum number of modules to be connected in series, maximum number of modules to be connected in parallel, and also the maximum number of these strings to be connected in parallel. Okay. And let us now see the different possible arrangement of module array. Already I have prepared this table where possible arrangement of number of modules per string and number of strings per array at two different power outputs. One is at standard test condition and other one is at the rated power output. So, when the rated factors like manufacturing tolerances, temperature and dirt are considered, what will be the rated power output, which is about 230.137 watt, and for standard test condition it is 300 watt peak. Okay. As calculated before, the minimum and maximum number of modules per string are found to be 12 and 22. So, for the case of 12 modules per string, and as we know the maximum number of strings per array is 69. So, if we multiply 12 with 69 and then 300 watt peak, then what we will get is 248.4 kilowatt. Okay? And same calculations if we make, then 12 multiplied by 69 into 230.137, then what we will get is 190.55 kilowatt, right. So, we can have one more combinations like 22 multiplied by 69 and multiplied by 300, then what we will have, it is about 455.4 kilowatt. And if we consider the rated parameters, then output will be about 349.35 kilowatt. Okay? And we will have more number of combinations and we can select the best one, but we must keep in mind that what is the input power for the inverter. Okay? So, inverter power requirement is 280 kilowatt. So, we need to provide energy just near to 280 kilowatt. Okay? So, that way we need to find out the best combination. So, we can have something like 22 number of modules per string and number of string per array 55. Then what we will get if we consider the rated power, which is equal to about 278.46577, okay, which is very close to 280 kilowatt power, which is the input to the inverter. Okay? Or we can think of another class if we do not consider the rated power, something like 22 number of modules per string and 42 number of strings per array. So, under that condition what we will have, we will get power output close to 277.20, okay, which is also close to 280 kilowatt, right. So, we can consider this or maybe this, or we can think of some other alternatives. Okay. So, the other alternative combinations are something like 16 number of modules per string and 58 numbers of strings per array, which gives power output under standard test condition is 278.4 kilowatt. And if we consider one more category or combination, that is 20 number of modules per string and 60 number of strings per array, then what we will get 276.16 when we consider the rated parameters. Okay? So, there are multiple combinations. So, we need to find out the best combinations for maximum output power. And if we consider these two cases, for a 2 megawatt power plant, the number of modules required will be about 6667 for the first case, this case, and for the second case we will have 8691 numbers of modules. So, how we will get it? Say for example, in this case, so 16 multiplied by 58, which is equal to 928. Okay. So, that many number of modules are required, okay, for this combination, and this gives about 278.4 kilowatt, right. So, for 278.4 kilowatt generation power output, we need about 928 number of modules. Okay. So, for 2000 kilowatt the number of modules required can be easily calculated. Okay. So, this will be something like 928 multiplied by 2000 divided by 278.4. Okay. So, which is found to be about 6667. On the second case, similarly we can find out the number of modules required is 8691 numbers. Now, for this 2 megawatt power plant, the number of inverter required can also be calculated. As we know, this rating is 250 kilowatt. Okay. So, 2000 kilowatt divided by 250. So, it will be, this will be kilowatt, 8 numbers. So, minimum 8 numbers of inverters are required for a plant having capacity 2 megawatt. Okay. So, this is how we can design a solar grid connected PV system. Okay. There are many components. What I left, maybe this can be considered in the next class when we analyze the performance of a grid connected PV system. Okay. So, we can summarize what we have discussed in this class. We understand the design of a grid connected PV system, then the operating temperature of the module plays an important role in matching PV arrays with inverter, that also we understood. The voltage, current and power ratings of modules and inverters are the 3 criteria which ensures a proper matching of the system in terms of performance and safety. Okay, that we have clearly understood. And the kind of design methodology we have adopted here, first we tried to calculate this derated module or derating of modules, how derating of module takes place, what are different factors, then minimum and maximum operating temperatures of the modules, then minimum and maximum effective voltage of module, then lower and upper limit of strings, okay, then matching of current rating of modules with inverter input current ratings to determine the possible string to be connected in parallel, and finally, the possible arrangement of module array we have studied, and sizing of inverter based on the size of the array, that we can understood now, and also we have demonstrated how to design a grid connected PV system. Okay. So, thank you very much for watching this video. Thank you.